Welcome back. In this short lesson we will learn a little bit about the nuclear data library for Serpent. The nuclear data library, which is also called neutron cross-section library, covers the neutron energy dependence of different data for basically all the existing nuclides. So this library contains primarily the neutron cross-sections, all kinds of cross-sections. So you will find their total cross-section, the absorption, fission, inelastic scattering, elastic scattering, capture, proton production, the alpha production, N2N, N3N reactions, and so on. Apart from the cross-sections, the nuclear data library also contains some other information, such as the energy and the angular distributions of neutrons that went through some specific reactions, such as the inelastic scattering or N2N, N3N reactions. We cannot calculate the scattering angles for these reactions, so these have to be measured experimentally, tabulated, and we use the distributions from the cross-section libraries in order to decide what is the scattering angle for these neutrons. As for the format of the nuclear data, the Serpent code is using the so-called ACE format, which is common to a number of other codes, among others the MCMP. So the ACE format actually was developed for the MCMP code, but other codes are adopting this format as well. It's convenient to use the same library for different codes. The ACE format library contains data of three types. So the type 1 data are the continuous energy neutron cross-sections. These are also called sometimes the point-wise cross-sections because the dependence on the neutron energy is tabulated, so it's present in the library for different values of the neutron energy, and this dependence may be described by several hundreds or thousands or hundreds of thousands points. So it depends on the specific nuclide and the specific cross-section what number of points is needed to describe the energy dependence. So nuclides such as the hydrogen contains very simple dependencies of the cross-sections on neutron energy. So in case of such nuclides, very few hundred of points are only needed to describe the dependence very accurately, but some other nuclides such as uranium or plutonium require many more points, so hundreds of thousands of points are needed. Apart from this type 1, there are two other types of data. The type 2 data, we are not going to need this is just for the dosimetry calculations, but we are going to use the type 3 data, which describe the thermal scattering cross-sections. The thermal scattering cross-sections are compiled for specific materials, not for specific nuclides, and this is because the chemical bound in the molecules is important for these materials for low energy reactions where the neutrons are basically thermalized already. So the chemical bond within the molecules is changing the relative speed between the nucleus and the neutron. So these thermal scattering cross-sections, they are kind of corrections to the type 1 data in the library. The nuclear data library in the ACE format can be generated by the so-called ENJOY code, which is a Los Alamos code, and you need a special license in order to use this code. It's possible to get it, but you have to apply for it and receive the license. The Enjoy code can generate these ACE format libraries directly from the nuclear data library in the ENDF format. So these libraries, they are publicly available, and you can freely download the ENDF format libraries produced from different countries, from different institutions. So you can get American libraries, which are called ENDFB. There are Japanese libraries, European, Russian, Chinese. None of these libraries are perfect, and they all contain errors. And actually the errors that are coming from the nuclear data libraries are contributing quite a lot to the final error in our results. So it's interesting to compare different libraries. Now we don't have to generate the ACE libraries ourselves, because the Serpent code comes equipped with the ACE libraries, and you will find them generated for a number of material temperatures, and they will use different sources for this data. One is European JEF library, and then there will be also American ENDFB library. So you can choose what library you want to use, whether the European or the American. All the nuclear data for different nuclides and for different temperatures could be in principle present in a single file. However, this is typically not the case. Usually one file is created for a single nuclide and for a single temperature. So we have usually the libraries in form of hundreds or thousands of files. So we have one file for hydrogen at specific temperature, let's say 0 Kelvin. Then we have another file for hydrogen at let's say 300 kelvins. And then we have hydrogen for 600 kelvins. Right, for every possible nuclide we have a number of files. So we have also files for uranium-235. You will have a number of files for different temperatures, for 300 kelvins, 600 kelvins, 900 kelvins, and so on. And the fact that there are so many files describing the cross-sections for different nuclides at different temperatures, that is a complication to us. Let's say we have our input file, let's say this is our input file, and we have a number of nuclides in all our materials. We may have several dozens of different nuclides describing the materials of the fuel and the cladding and the coolant and all the construction materials. And in principle, we need to associate each nuclide with a file in which the cross-sections for this nuclide at the specific temperature are present, right? So we would have to establish links between these different nuclides in the input file and the files, which may be in principle scattered over the whole file system. So we would have to write the path to the files in the file system in the input file. That would be a very cumbersome process, because we would have to check where the cross-sections are present on the hard drive. So in order to avoid this mess in the input file, another file is introduced. It's called the directory file, and it stands in between of your input file and the cross-section library. So in these directory files we have inputs for different cross-section files. So each file is associate it with specific nuclide. So we have a name of a nuclide, and then this file includes a link, pointer to the file where we can find it. So different nuclides at different temperatures are given different names, right? The name for hydrogen at 0 Kelvin will have a different name than the hydrogen at 300 kelvins. So this directory file will contain many lines. Each line will be devoted for one nuclide at specific temperature, and it will contain all these links or path to the different files in the file system. So typically the cross-section library comes with the directory file, and all you have to do in your input file is to have a link to the directory file, right? Once you have the established connection between your input file and the directory file, you can use the names for different nuclides at different temperatures from the directory file. So we can associate our nuclide with the library through the names from the directory file. So we need to check the name of the nuclide at different temperature in the directory file, and we have to use these specific names in our input file. Let's have a look closer at the structure of the directory file. The structure is very simple. Each line is devoted for a specific nuclide at a specific temperature. It contains a number of parameters. The first one is the alias name. That's basically the name by which you refer to this nuclide at your input file. The next parameter is the name by which the nuclide at the specific temperature is identified at the cross-section library. The next parameter is the type of the reaction, type 1, 2, 3, so this is just an integer number. The next parameter is the nuclide identifier. It's calculated according to this formula, so it is an integer number. In this formula, Z is the number of protons and A is the mass number. So for instance, for hydrogen 1, the ZA nuclide identifier is 1001. This identifier for instance, the uranium-235 is 92-235. Some of the nuclides which may be present in our system may be metastable, and they may have different cross-sections than the same nuclides in the ground state. Therefore, we need some way to separate between the ground state and the excited states of different nuclides. So the isomeric state is described by this input I here. If it's 0, then it's ground state. If it's 1, then it's excited state. The next parameter is the atomic weight of the nuclide. The next parameter is the temperature in kelvins for which the cross-sections were derived. So this is very important. When you need to find the name for a specific nuclide for a specific temperature, you need to basically check this nuclide identifier and the temperature, right? And once you have located the correct nuclide, the correct cross-section, you just use this alias name in your input file. The next input here decides whether the cross-section is in the binary or ASCII form. If it's in the binary, then the input here is 1. If it's in the ASCII or text form, then the input is 0. We have all the cross-section in the ASCII format, so you can basically open it in any text editor and look at the data. When it's in the binary format, then you cannot easily display the data So that is the disadvantage of the binary cross-sections. However, there is also an advantage of using the binary cross-sections, and that is the speed at which they can be processed. And the last parameter is the path at which the cross-section library is present in the file system. So this gives the link between the location of the cross-section library and the name of the nuclide. So if you by chance change the location of the library, you'll have to make a change in the directory file at this place. So here we can see an example of a part of the directory file. The directory file contains thousands of lines. We can see only few here. Let's have a look at the first line. Here we have the ZA identifier. So from here we can see that it's hydrogen, and we can see the temperature 600 kelvins, and we can see the path to the cross-section library file. So you can see that it's present at the folder XS. So when we look at the alias name, you can see that the ZA identifier is actually reflected in it, and then there is a dot, and after that there is 06, which in fact relates to the temperature 600 kelvins. This is very convenient for separating different nuclides at different temperature. We can write the temperature into the name, and then the C means that the cross-sections are continuous. When you look at the second line, you can see that it's exactly the same like the first line, except of the very first parameter, the alias name, which differs to the first line. So as you can see, you can have multiple inputs in the directory file. In case that you want to have more alias names for the same nuclide at the same temperature, you can, in your input file, you can either describe it by this name or by this name. You can choose which one you like more. So then we can see more inputs for oxygen, and what's interesting here is this input for zirconium. You can see that the ZA identifier for zirconium is a little bit strange, because it doesn't conform to our definition, right? It ends by 3 zeros, while there should be the mass number reflected in it, and it's not. That's because this does not relate to a specific nuclide, but the cross-section file is derived for a mix of nuclides. It actually reflects the natural composition in the zirconium. So zirconium is naturally composed of a number of different nuclides. So we very often use zirconium in the cladding. So we would have to specify different nuclides of zirconium at different densities. So that would be a lot of work for us. So instead we use the cross-sections which are compiled for a mix of nuclides. So that's very convenient for us. So whenever you see a nuclide ending by 3 zeros, that means that it relates to the natural composition. So almost all these cross-sections are of type 1, except of the last 2 lines, where the second to last line relates to the thermal scattering cross-section for light water. So that's type 3 data. And that is all for this lesson. Have a nice day.